Today, I will be presenting my project, Flow Heterogeneity Impact on Dissolution Processes in Geologic Porous Media. Before jumping in, I want to thank my advisor and collaborators for the immense help on this work, and I also want to acknowledge the funding source, the National Science Foundation, and the Petroleum Research Fund. A novel approach to achieve net zero emissions is the process of capturing and storing atmospheric carbon dioxide. One method to do so is geologic carbon storage, where we inject supercritical CO2 into a confined brine formation in the subsurface. The injected CO2 will acidify the host brine influent and then dissolve any carbonate present in the reservoir. Local reactions at the injection site may compromise the integrity of the well seal, potentially allowing CO2 to escape the confining caprock. Also, the resulting dissolution pattern can alter the mechanical integrity of the formation. This motivates us to better understand and model the impact of fluid flow on solid dissolution in these brine rock systems. Conventionally, dissolution behavior is predicted using the dimensionless transport and reaction metrics in the form of a phase diagram, namely the Pecklet and kinetic numbers, where the Pecklet number compares the advective to diffusion transport rate, and the kinetic number compares the diffusive to reaction rate. The most cited dissolution diagram from Golfier and co-authors studied the dissolution of granular salt samples and observed the following trends. When the transport and reaction timescales are well matched, we see a uniform dissolution pattern, where fresh reactant is carried away from the inlet and the reaction spreads throughout the sample. At very low Pecklet numbers, we expect compact dissolution, where the porous medium is mostly dissolved where the injection occurs. With greater kinetic and Pecklet numbers, we expect wormhole dissolution, where highly conductive channels are etched throughout the rock where all of the reaction occurs. To reiterate, this diagram was developed from observations of granular salt sample dissolution. The uniformity of the sample structure will result in a homogeneous flow field. However, real rock samples are rarely homogeneous. Let's plug some data of variably heterogeneous samples into Golfier's model. I'll show these points in blue. First, we plot the samples where we observe uniform dissolution as blue circles. All of the samples correctly fall into the uniform regime as defined by Golfier's diagram. Note, I am showing the post-dissolution structure where red is the reacted surface and gray is the unreacted surface. Next, we plot the samples exhibiting compact dissolution as blue squares and wormhole dissolution as blue diamonds, and we see apparent misclassifications. The complexity of these sample structures can induce heterogeneous flow and is a possible cause for this misclassification. Through this project, we sought to better understand what controls dissolution processes in structurally complex media. To do so, we first proposed models to predict the reaction ratio and dissolution behaviors. And then we investigated the feedback process of flow heterogeneity on dissolution behavior. We can determine the Eulerian flow field via direct numerical simulations. Now, there is no agreed upon metric to quantify the heterogeneity of this flow field, so we proposed one in our publication last year. We proposed to quantify the flow heterogeneity using the percolation threshold. The percolation threshold is a measure of flow channelization and divides the flow field into mobile and immobile regions. Mathematically, this is defined as the ratio between the minimum velocity in the mobile region relative to the average velocity of the sample. This velocity threshold is set at the first established path that connects the inlet to outlet. Velocities lower than this threshold are in the immobile region, and velocities equal to or greater than this threshold are in the mobile region. A small percolation threshold indicates that the first breakthrough particle speed is similar to the average and indicates a homogeneous flow field. A large percolation threshold indicates that the first breakthrough particle will exit the medium much faster relative to the average exit time, and indicates a heterogeneous flow field. Our hypothesis of why flow heterogeneity is key to explain dissolution can best be explained with this pore scale schematic. Here we have zoomed into the pore scale of a 2D velocity field. Once the flow field is determined, we can find the streamlines that show the direction a particle will travel, shown as white paths. Now we'll use the percolation threshold to divide this flow field into mobile and immobile flow regions, shown in white and blue respectively. When CO2 is injected into the rock, shown here as pink particles, the bulk of the injected fluid will travel through the mobile region. Here, the CO2 particles are most likely to come into contact with the host rock at the interface between the mobile and immobile regions. At this interface, shown in red, the acidified brine locally mixes with the rock and reacts to dissolve it. Since the acidified brine is not equally distributed in the void space, mixing of the reactants is incomplete. This is in stark contrast to batch dissolution, where a solution in a beaker and the rock are forcefully well mixed by a stir bar. To gauge how incompletely mixed and underreacted a system is, it is typical to quantify a porous medium's reaction ratio, the ratio between the measured or effective reaction rate to the batch reaction rate. Returning to the apparent misclassification by Goulfier's diagram, we see that the blue samples require the percolation threshold as the third dimension to correctly be classified. When viewing this from the Pecklet number and percolation threshold plane, we can arbitrarily draw cutoffs to divide the three behaviors. We can see there is a relationship between the Pecklet number and the percolation threshold, and we can quantitatively confirm that with the following model. To statistically determine the best combination of the available metrics, we used a generalized linear model, which produces a flexible linear equation that will predict the expected value of the reaction ratio as a function of some combination of the Pecklet, kinetic, and Domkeller numbers, as well as our flow heterogeneity term, the percolation threshold, and other metrics like the mineral heterogeneity. All of these terms are additive as either independent or interactive terms. The various formulation combinations are tested and ranked by their AIC, which balances over parameterization and goodness of fit to identify the best statistical model. The best model we found so far is the linear combination of the percolation threshold and the Pecklet number. Here shown are the results of the predicted space for the range of Pecklet number and percolation threshold that we have been working with. Blue indicates lower reaction ratio, red indicates higher reaction ratio. On the plot on the left, we can appreciate that this does a pretty good job at capturing the reaction ratios for our heterogeneous structures. In the plot on the left, the marker size indicates the magnitude of the reaction ratio, and the marker color indicates the observed dissolution behavior. Immediately, we can see the relationship between the reaction ratio and dissolution behavior, where larger reaction ratios are associated with wormhole dissolution, and smaller reaction ratios are associated with wormhole dissolution. So while this model explicitly predicts the reaction ratio, it also hints at the expected dissolution behavior. Because we have the structural evolution of our samples, we got interested in looking at how the flow was arranged as dissolution progressed. Here is a plot of the initial on the X and final on the Y metrics for flow heterogeneity. Remember that low values indicate a homogeneous flow and high values indicate a heterogeneous flow. From this, we see generally that initial homogeneous flow perpetuates uniform dissolution and initial heterogeneous flow perpetuates wormholing. We deem this behavior reinforcing. However, in contrast, we also have regulating behaviors where we will start with either homogeneous or heterogeneous flow and end up with the other. So we see that some of the structures switch regimes during dissolution, and we suspect a distinct structural shift is happening during the dissolution, though we are unsure of what that is, and we will evaluate that in further work. The key insight from this work is that dissolution reactions are controlled by transport and reaction timescales, but their baseline hinges on flow heterogeneity. And we determined that for complex structures, that we must account for flow heterogeneity in addition to transport and reaction timescales to predict dissolution behavior. And we can predict the reaction ratio as a function of the Pecklet number and percolation threshold. And we generally see a positive feedback process between flow heterogeneity and the resulting dissolution pattern. Thank you.